Now, what I'm doing here is we're going to look at a problem where it asks you to create a rule, okay? Now, the rule we're going to try and find here is for how many squares do we need how many matches? Now, the difference from having individual squares on their own is that obviously the connected squares share a side, which means that the first square on its own has all 4 sides. But you'll notice that when we have 2 squares connected, there's only 7 and not 8. And then when we have 3 squares, it becomes 10, when you would expect to have 12. Now we need to come up with a rule for this. How are we going to go about it? Well, I'll show you. Now, the first thing I'm going to do is work out the relationship between these 2 numbers. What do I do to the 1 to turn it into the 4? The 1 being the output, the 1 being the input number. And I've just made my really tidy table untidy. The 1 is the input number, which is the number of squares. The 4 is the output number, which is number of matches. How do I turn this 1 into 4? Well, let's call squares S. And let's try S plus 3. Because 1 plus 3 so it works for that. How about when we substitute 2? Now, substitute is where we put a number. This is our pronumeral. When we put a numeral, which is just a number, when we substitute a numeral for the pronumeral. Okay, we've already done that with the 1. Let's try 2. Plus 3 equals 5. But our number of matches is actually 7, and you can count them. We've got 7. So that rule is no good. All right, what can I try now? 2 plus 5. Let's add 5. Oh, no, hang on. We can't add 5 because we already know that 1 plus 3, we're only adding 3 here. So maybe we need to multiply something. But even just multiplying something, if we multiply 1 times 4, 2 times 4 is 8. That's not going to work. So maybe there's going to need to be 2 parts to our rule. So let's look at 3. 3 squares, 10 matches. What can we multiply 3? Well, we don't have 10 as a multiple of 3. So we're going to have to add something or subtract something. So what if we try S, which is our squares, times 3 plus 1. Let's try that. So we're now going to substitute the 1, the 2 and the 3, which is our square numbers, into where we have this pronumeral.
I'm trying to listen to Stu. This is very confusing.
Just hang with it. We'll do questions at the end. Just for now, I'm just giving you a sample of how to do this. So let's try 1, where the S is. So 1 times 3 plus 1. And I use this symbol to tell you that I'm going to another line to solve this. So 1 times 3 is 3 plus 1 equals 4. So when our side is 1, so that actually works. But it works for 1. So that one is okay. Now, let's substitute the 2 squares into our rule, okay? because this is our rule. Let's use 2 times 3, because that's 2 squares, plus 1.
Where are we going?
Just watch on screen. 2 times 3, 6, plus 1, 7. So when we substitute the 2 where the pronumeral is for our rule, 2, we expect the answer to be 7, and it is. Okay, and I'll write that in purple. So we know that the rule is true for 1 square and 2 squares. Do we think it's going to be okay for 3 squares?
Yes.
All right, well, let's find out. So when we substitute the 3 for the S, we multiply by 3 and add 1. 3 times 3 is 9, plus 1 it is 10, and we already know it's 10. So our rule works, okay? So basically what our rule tells us to do is get the number of squares, multiply it by 3 and add 1. So 1 times 3 is 3, plus 1 is 4. 2 times 3 is 6, plus 1 is 7. 3 times 3 plus 1 is 10. So part 1 of the problem that you'll see in your text shortly is constructing a table. Part 2 is constructing the rule, and part 3 is calculating for 20 squares. Now I'm just going to stop the recording and we can have some questions.
Mr.